Hello again, this is Dr. Trevor from physicsthisweek.com. Today let's talk about some momentum problems and take a look at some solving solutions for, in particular, perfectly elastic collisions. So we've got two identical objects placed on a frictionless surface. One approaches the other, we're given its speed, and the objects collide and stick together. We want to know what the speed of object 2 is after the collision. So anytime you approach one of these, you want to draw a diagram of what's going on with the problem. So we've got two objects. I draw this slash in here to show that something has happened. In particular, it's the collision. And now I've kind of got my objects together. I see these two are stuck together afterwards. I'm going to put my positive direction to the right as we traditionally do. And then I'm going to make a list of the variables that I'm going to probably use in this type of a problem. We've got two objects, m1 and m2, and each of them has an initial velocity and a final velocity. So we're not looking right at the collision, we're looking just before and just after. So this is the initial case, this is the final case. Now we're told in this particular problem that there are two identical objects. When we see this, this is physics code for they have the same mass. So I do a little trick here. M1 and M2 are equal to each other. I'm going to set them equal to a third variable, M. That way I see the same thing in each place, and if I have an M1 in my numerator and M2 in the denominator, I can cancel them out because I see the same label there, the same variable. Notice that we're not given any particular mass. That may or may not make a difference depending on the problem. Okay, we are told that the first object goes with a speed of 3 meters per second. We're not told which direction, so we're just going to pick one. We are told that the second object is standing still, so I've drawn an arrow for the first object. I have no arrow for the second object because it's standing still. If you want to put v equals 0 right here, you're more than welcome to. In fact, that's oftentimes helpful. Okay, we are then told we are asked what is the speed of the object 2 after the collision. Because these two guys stick together, that again is code that they have to move together. If they aren't stuck, one will move away, meaning it has a different speed than the other. So we're going to give them both the same speed. V1 is equal to V2 final, which is equal to VF. Again, I put those guys in where I see V2F and V1F. And I've drawn it up here. The other thing I want to do before I go any further with the problem is to think about what's happening here. I've got an object that has some speed, some momentum, and I have a second object that has no speed and therefore no momentum. After the crash, I still have the same amount of momentum, but I've got a larger mass that's moving. That's a hint to me that chances are the speed is going to be lower in the second case. So if I write down the equation for the conservation of momentum, the other thing that I notice is this is a vector equation and the two sides are equal, which means that they have to be the same size and they have to have the same direction. That's yet another clue that this forward direction is the correct way to do it. So I'm going to take and write out the pieces of my momentum. And now I'm going to change this into an algebra equation, just like we did before with force equations. Notice here that M1 and M2 are both equal to M, so I'm going to substitute those in right away. V2 is moving at 0 meters per second. I'm going to put that in right away as well. I only ever put zeros in at this stage. Oftentimes that gets rid of a term so I don't have to worry about it from here on out. Notice that after the crash, these are moving in the same direction. They're moving at the same speed. They have the same mass. So I've got two of the same term. The other thing to notice here is I didn't really give a sign to either of these two speeds. I have it kind of assumed up here in my diagram, but I haven't given a specific sign to these. it's very possible that one of these, or actually both of them because they're the same variable, could turn out to be negative. We'll let the math take care of that. Because both of these have a v final in it, I can factor that out. So I have m1 plus, or m plus m times v final. Again, my zeros up here, I've just carried this side down a little bit further. And I'm solving again for v final. That's the one that I'm not sure what it is, so I want to isolate that, get it by itself. So I divide both sides by m plus m. And notice here now I've got m on the top, 2m's on the bottom, and in fact I can write it that way as m and 2m. The m's cancel out, so I'm left with v final is v1 initial divided by 2. In this spot, I'm going to put in the 3 meters per second. I took care of the directions back here by giving this a positive and giving this no sign at all. So now I'm ready to plug in my numbers. I've got 3 meters per second divided by 2. The units for this one is easy. I only have meters per second. 2 is a whole number. So my final answer is v final is 1.5 meters per second. It's probably a good idea to give your professor a hint here that you know what you're doing by actually writing a sentence that states what your answer is. The two objects move together to the right at 1.5 meters per second. So if you did something strange like put your positive direction in the backwards direction, the professor reading this would see that it's still moving to the right. Hopefully that works out with his solution, that it's moving to the right. And of course, box your answer at the end. Okay, let's take a look at a slightly different problem. Again, we've got two identical objects. They're placed on a frictionless surface. One has a speed of 3 meters per second. The other has a speed of 2 meters per second. So I've got my drawing. I've got my variables that I want to find values for. Again, because they're identical objects, I put in my m without a subscript because m1 is equal to m2, and I've set that equal to m. They stick together again, so the v final is the same. Notice this time I've drawn my v final just a little bit smaller. Okay, the first object again is moving at 3 meters per second, but this time the second object is moving at 2 meters per second, and it's moving in the backwards direction, at least according to my coordinate system that I've got set up. So this time I've drawn it smaller because this one actually has a negative momentum as compared to the previous case where it had 0 momentum. So that means this guy's even going to be moving slower as a collection afterwards. So I draw in my initial and my final momenta, the conservation of momentum. Draw out the individual pieces of that as a vector equation, and now do it as a algebra equation. Again, m1 becomes m, m2 becomes m everywhere that I see it. v1 initial is positive, v2 initial is negative, so I bake that right into the equation right up front. v1 or m1 and m2 are moving together afterwards, so I've got the same type of situation here. I've got m's in each term, I've got v finals in each term. I'm looking for v final, so I'm going to join those two together, and I'm going to factor out an m from each of the terms on the other side. My m plus m becomes 2m. When I divide on both sides, it drops to the bottom. I've got my m from above. And once again, the m's cancel. I'm left with a half. But this time, I don't just have v1 initial. I have to take care of v2 initial. But I'm all ready to put the numbers in. I've already got my signs here. That's why back here, I didn't give it a negative sign. I've found when I teach students to put the negative sign here, they see the negative and they put it in and they end up subtracting a negative and adding it again. So again, let your directions take play in the picture, and in the algebra equation, just put numbers in at the very end. So 3 minus 2 is just 1. Multiply that by a half and I get 0.50 meters per second. Again, the units are simple because I'm just dividing by meters per second. Write down your sentence explaining what's going on. The objects are moving together to the right at 0.5 meters per second, and box your answer. Just a quick note on significant digits. I started out with 2 significant digits everywhere. I do a subtraction here. This number is a whole number 2, so when I divide by a whole number and I have 2 significant digits here, I need 2 significant digits in my final answer. So just in review, read the problem to make a list of known and unknown variables. Make sure you draw a diagram to show how those variables relate to one another, showing the specific directions if things are stuck together, and try to make a guess on the relative sizes of the speeds if you can. Then make sure you apply the law of conservation of momentum and carefully change from a vector equation into an algebra equation by including directions for plus or minus. So in this problem above, V1 would be positive, or V1 initial would be positive, V2 initial would be negative. And as always, only enter zeros. Wait until the very end to enter numbers. That way you make your calculation a lot easier at the end, and you are likely to find out situations where you can do things like cancel out the masses. So this has been Dr. Trevor again for physicsthisweek.com. Remember, you can always visit us for all kinds of help with physics. And if you're watching this video on YouTube, please give me a thumbs up. I really appreciate that. And thanks for stopping by today.